So up to this point, we've been really reviewing, introducing the lecture, or introducing the course, and so far our lecture has taken us through revisiting some basic terms. And we're going to pick that up again tonight and finish it out. And as I said earlier, we're going to move on into some new material, which is equilibrium. We've not really discussed that as a topic per se. I don't believe up to this point throughout the program. Anybody had a classroom discussion on equilibrium that you recall? Okay, good. So it's new material, and we've added it to the end of this lecture, and it's identified as new material. So we'll work through that tonight, and as our time permits, we'll move into the next lecture. If not, then what we will do is we'll reschedule that first exam, as I said earlier. But we'll communicate all that. Before we get started in the lecture, though, we want to start with a safety topic. And this one I found, I was looking online, and I found a report, a study that was done by Purdue University, I believe it was. It was a fairly lengthy study, and what they did was they studied instances of fires at gas stations, at the pump, at the car. And they did a lot of analysis on that and studying on it. And here are some of the statistics that came out of it, and then we'll share about some of the research. 78% of those fires that occurred at the pump as people were pumping, 78% of that occurred, they were female drivers. Now, this is not a female joke or anything like that. That's the statistic. Okay, 78%. Now, of course, that kind of gets the researchers going, whoa, what's going on, what's different? And so, I told you, it's not a joke about women drivers, okay? So, the research, they went and they reviewed these surveillance film, and there was a video with this, but it was so, grainy and everything, you couldn't really make it out for displaying here, so I opted not to use it. But they had these surveillance cameras, at the gas stations where they show the pumps out there, and almost every single one of the female drivers had this in common. They get out, go back to the pump, scan their card, whatever, start the pump, and then they would get back in the vehicle. Now, why would that cause them to have more fires, do you think?
They build up static electricity.
Exactly. Well, why didn't they spark it to begin with?
Because they ground it out and they hit the ground.
Yeah, when they get out, and everybody does it, when you get out, you've done it in the wintertime, pow! The big electrical discharge that you get, because you're touching the metal, you're touching the door. But what they found out was that women, by and large, would leave the door open. They'd get out, and then if they had a card, they probably would get back in the vehicle, put the card away, do something in their purse. Then they would get out again without touching any metal and grounding that static electricity. And so when they went back to the pump and went to reach for that metal nozzle, they get an arc. And that is what ignited the fire. Now, what do you think, regardless if it was man or woman, what do you think the first response to a flash fire at the nozzle is? Exactly. Pull it out. Pull it out. And like I said, this is man and women did this. Pull it out, and it's usually in what position? The locked on position. And some of you are really smart like me. I figured out how to take care of those that didn't have the little lever. I stuck my gas cap in there. And wedged it in there so that it would. So now it's wedged in there with my gas cap, and I'm spraying gas all over the place, and the fire just gets out of control like that. And so what they obviously recommend is that you make sure that you ground yourself if you do get back into the car. Before you go back to the nozzle, make sure that you ground yourself. Don't use your gas cap for the automatic kickoff. And definitely in a flash fire, do not pull the nozzle out unless you shut it off first. If you can do that, shut it off first and then get it out of there. one of the things, since I did this study, I've been watching people at gas stations. And you know what? It's true. Watch people. Women most often get out, leave the door open, and go around, and then they will go back in and again leave the door open. I was telling my oldest son Saturday, we were at a gas station in Atlanta, and I was telling him about that study. There was a lady in front of us, and I said, watch her. And exactly as I described it. Now, some guys do that too. Okay, he did that. Even after I told him. He got out and left the door open. And came back and put his you know, he keeps his wallet in the door. He put his card back in his wallet, put it down, and I said something, and he, oh yeah, golly, yeah. But it's interesting. It really is. So that's just unreal nuclear power whatsoever. But it's the kind of accidents that can be prevented, avoided, and certainly that's a devastating accident. That's pretty significant. Just by following a few simple things as you're going about that daily task or that common task that we all do. So let's get started with the, I think the last topic that we talked about, you know, help me out if it's not, we specifically talked about specific activity and illustrated that that puts activity in terms of mass. Let me back up to maybe. There we go. Puts it in activity per unit of mass, whether it be grams or kilograms or whatever, curies or becquerel, it doesn't matter. And it helps us kind of gain an appreciation for really the fact that one curie of one isotope and one curie of another isotope does not relate to the same volume. So in comparison, we did and showed you what the specific activity was for cobalt versus uranium. That's here in a little bit. It's all based on radium, though. Radium was the standard. 1 gram of radium is 1 curie. And so the specific activity is 1 curie per gram for radium. And the mass material that is required to produce this disintegration rate, which is the definition of curie, 3.7 e to the 10th disintegration per second, will be a function of the number of atoms per gram of material. Gram atomic weight, or another term for gram atomic weight, is mole. I think y'all experienced interaction with mole and gram molecular weight on your homework. That was one of the keys to solving those problems, was coming up with that relationship. So putting it as an example, we talked about 1 curie of pure cobalt-60, nothing else, just cobalt-60, with a half-life in excess of 5 years, 5.27 years, has a mass of 0.9 milligrams. Not a whole lot at all, less than 1 gram of material with 1 curie in it. Highly radioactive, concentrated in a small source of cobalt-60. We can take that same activity measurement, curie, and look at a load of natural uranium-238, half-life 4.5 e to the 9th years, and you can see that it has mass of more than 2 metric tons. Significant difference. Same activity measurement, but certainly a huge difference in mass. You can also use this as an illustration of a thumb rule that basically tells you that the shorter the half-life of the radionuclide, the greater the specific activity is going to be. That's just a rule of thumb. We then, moving from specific activity, we're going to move on into this area of radioactive decay law. Now, you've been functioning with this for some time, since 103 actually. It was introduced there. It was introduced and expanded upon in 113, and it's back. It's still here. We're still going to talk about it. Except now we're going to show you really where it was derived from and talk a little bit more about that. Because in understanding where it came from, you learn some useful tools for working some of the issues that you may face when you're doing transportation placarding calculations and stuff. So let's take a look at it. Radioactive decay law. It is the rate, which means it's some unit of time, right? That isotope, the radioactive isotope will decay. At what rate does it undergo this disintegration? And that's the term D per S, or D per M. Disintegrations per second, disintegrations per minute. Interesting to note that it is unaffected by any of the physical forces like temperature, gravity, or atmospheric pressure. It is a constant. U-238 decays at a specific rate all the time, regardless of the situations that you place it in. Same for any of the radioactive isotopes. Now, if I'm going to describe that radioactive decay, I can describe it regardless of what mode of decay occurs, whether it's be an alpha decay or a beta minus or a beta plus or electron capture. It does not matter. We can express it the same way, and that's what makes it very useful. In that, talking about the activity, we don't have to make accommodations for the type of decay that occurs. It's the same equation. And what it does is that it allows us to express a change in the number of atoms that occur over a unit of time. Number of atoms that change over a unit of time. And I may have already covered this, I'm not sure, but we'll just refresh you on it. What does this symbol here mean? That's what it stands for. What does it mean? Change. Right. So change in the number of atoms is equal to minus lambda, which should be very familiar. What's the name for lambda? What is it?
2693 divided by the half-life.
No, what is it? Lambda is the Greek alphabet we use to represent it. But what is lambda? Decay constant. That's exactly right. And mathematically, it is 0.693 divided by the half-life. That's correct. So we have a minus here because it's a decay occurring. It's a drop or decline. So we've got our decay constant times the number of atoms times this delta T, change in time, the amount of time that has lapsed. So that's where we're going to start with this. That's the beginning of the definition of our radioactive decay equation. We take it on. And manipulating the equation a little bit, we can change, get the delta time, the change in time over here, and get this term, change in number of atoms per change in time is equal to minus lambda n. That is activity. That is activity. Delta n divided by delta t. And so we can rewrite the equation. Activity is equal to lambda times n. We can drop the minus for this one. We can drop the minus because it was just there to remind us it was a decline. And this is our new equation. This is a base equation that you would have used in 2 of the homework problems, at least 2 of the homework problems, in which you wanted to, I think both of you had to come up with this n, and then bring it back to this base equation. Now, there's this thing in math called derivatives, and if we take and subject that to calculus and do a derivative on it, we come up with this equation. If you want to know how, and if you're a calculus-based person, and you just really love that stuff, I'll let you look in here, make copies of the pages that he shows you how that's done using calculus. That was first, I may have already told you, I don't know. First grade I got in college, in my bachelor's work, was in calculus. I hated it. Just couldn't get there. Just didn't click. I got a C. Okay, so that's the newest form of that after we send it through that derivation, the calculus. And it's just this, everything is as we know it to be. This is the number of atoms final, or the number of atoms after this amount of time. The original number of atoms times e to the minus lambda, that's the definition of lambda, times the time. Now, review question. What's the units on lambda? What's that, Colby?
Per time?
Per time. Per unit of time. It's per seconds, per day, per year, per hour. Because this top is unitless. That's where I get it. Right? So half-life, whatever it is expressed in, and we'll take and put the units on lambda as per unit of time. So when I do this calculation here, that multiplication of my time cancels, right? So the exponent of e is always unitless. This part of the equation is always unitless. No units. But you have to resolve that here before you get very far. Otherwise, you really mess up your calculations. So if half-life's in days, you want to put time in days. Or if half-life's in years, put time in years. Whatever. Units have to be consistent. So that's our first step. We take it there. And then, well, actually, not then. We go back here, and we're going to pick this up, because we got to figure out how to do this, how to come up with that n. Now, if we're given a sample and we know what the isotope's in it, and you can get that, you can get that by as a measurement, it's a mass spectrum. What is it, Richard? Spectrometer? Yes, thank you. Mass spectrometer, where you can identify the specific elements that are present in the sample, and by that you can also come up with weight. So you can do this, but then by doing that, we're able to come up with some reasonable facsimile of what the activity of that sample would be. So if I've got a sample, let's say it here, we're going to work with 1 milligram of cobalt-60. And if I want to determine what the activity is that's present there, I can take it through a couple of little manipulations, come up with this N. I can find that because I know the half-life of cobalt, or I can find it, cobalt-60, because that's a public value that's in our comparative nuclides. I can come up with the activity that's present. So the first step, I need to come up with the number of cobalt-60 atoms that are present in my sample. And this is the one that you just kind of, for doing homework, you had to really dig to find the answer. There were, I think, a couple of examples in the reading that showed you. And but what I'm finding out is we maybe have a weak area as far as providing you some basic terms. So we'll find out how y'all did on that, and because we have this same, we teach the same thing in 103 now. And I think we're finding out that we're not having defined all the terms for them. So y'all help me. So I got this set up. Using ICADE, what's the central question?
What's the activity?
What's the activity of?
1 milligram of cobalt-60.
1 milligram of cobalt-60. Okay. What information am I given? Well, not a whole lot, right?
Yes.
I got 1 milligram, but I've got this. I know it's cobalt-60, and I can get a lot of information from that. I've got this equation that I'm familiar with. And so, coming up with that, I can come up with my lambda based on cobalt-60, but then I need to come up with the number of atoms. We need to take the number of atoms and identify that by using this base equation. This is the gram molecular weight. And gram molecular weight of a single atom is really due to the weight of that isotope and the constituent parts of it, right? That's the way you would come up with that. Now is where you find a little bit of difference on how people might approach the problem. But this is called gram molecular weight, which tells you the number of grams in a mole of cobalt-60. And then I apply this. This is a constant. Avogadro's number of atoms is, by definition, there are an Avogadro's number of atoms in a mole of any particular isotope. Now, Avogadro's number you can find published in a lot of different places. It's 6.023 e to the 23rd. And two decimal places is fine. 6.023 e to the 23rd atoms per mole. So really, we're given this. That's a constant. Finding n boils down to coming up with this number. Right? Now, how would you think that you'd approach coming up with that number?
Chart nuclides.
Nelson?
Chart nuclides.
Okay. What are you going to do? What are you going to look for in chart nuclides?
Molecular weight at the bottom sometimes.
All right. That's a good place to start because there are a lot of the elements, a lot of the isotopes have that value, and it's always down at the very bottom. But this is not one of those. But cobalt-59 is. If you look right next to it, cobalt-59 has a weight. And what's the difference between cobalt-59 and cobalt-60? One neutron. Now, you minus a little bit because there's some binding energy that's used up when you stick a neutron in there. Binding energy is used, so you've got to lose some mass to give up that energy. So you can come up with that value by looking at the chart of nuclides, look at cobalt-59, and then add the mass equivalent of one neutron to it. That's one way you can do that. And you come up with that many grams per mole. What's another way? Anybody try something else?
All I did was
Huh?
add up the weight of protons, neutrons, and electrons together.
Okay.
But it's a little off because of binding energy.
Because of binding energy, right? You're gonna lose quite a bit because of the binding energy. But you can figure that out, right? Yeah.
Can you do an average of the 59 and 61?
You can do that. You can take 59 and 61 and take an average. Now, none of those are going to be precise. Let me just point this out. So if we were doing this, to win a Nobel Peace Prize or something like that, in radiation protection, we would want to come up with a little bit more precise method. But for our purposes, it's as long as it's reasonable to use here. 60 by itself is probably not good enough because that really kind of negates the binding energy. Robert, what do you do?
I went and asked you the constant, there's a formula you put at the bottom of this PowerPoint, using the constant, multiplying the times. You use 60 just because it was.
Yeah, I use 60 as the AMU because that's the A. Yeah. There is a constant that there is an equivalence between AMU and grams. And it's 6 point, do you have it there in front of you? I think I've got it here. It's, 1.6737 e to the 24th grams per AMU. So that's one way of doing it. But it all boils down to find out gram molecular weight. You could even Google it, okay? You can Google gram molecular weight of cobalt-60, you'll find it.
That's what I did.
Okay. So that gives us this number of atoms that are in that one sample, that 1 milligram. All right. The question, though, is what's the activity? So from this point on, it's going back up to that original equation, and I'm using the number that I came up with, doing another way, but it's kind of immaterial. I just want to use this to show the calculations. And I came up with a number like 1.02 e to the 19 atoms in that 1 milligram per wall system. Now my next step is to take the half-life that I can get from the charged nuclides and come up with my lambda, my decay constant. And that is simply the log of 2, natural log of 2 divided by half-life. That's 0.693 divided by 5.27 years, and you'll see 0.13 per year. I could have easily put that into days or months or whatever, it doesn't matter. But right now, I've got it expressed in this. So I plug that in, lambda times the number of atoms, and that gives me my activity expressed in atoms per year, or disintegrations per year. Same term, equivalent term, because we're talking about decay, atoms changing. And so I'm looking at that many atoms going away per year. Now this is not a common unit of expression for activity, is it? No. So let's try to put it into something we can use, which Curie would be a good one. If I get what they needed off this. This has been posted on Blackboard, by the way, this updated one. So we move on to conversions, and really from this point on, that's all it is. It's just unit analysis over to Curie's. So I'm starting at this activity. I'm wanting to go to Curie's. We often express that in disintegrations per second, so let's go there first. My number of atoms, time however many seconds in a year, gives me disintegrations per second. All I did was change the time units from years to seconds. And to move it on into Curie's, I then need to move it from this D per S into the Curie. This is my equivalent for that. 3.7 e to the 10th disintegrations per second per Curie. And as you can see, it's a little bit more than 1 Curie per milligram. Any questions? Moving it from A is equal to lambda n to Curie's. Okay. Ultimately, you do a little bit more math on this, and we're going to come up with this equation, which is the one we're familiar with using. So we don't have to go through the numbers calculation, the number of atoms. We've already further defined lambda, just repeating that, so we do a substitute here. And that's our radioactive decay law equation, radioactive decay equation. That's the one that you really need to be very proficient at. You should by now be able to take and solve this equation for any of the different components in the equation. You should be able to solve for T as far as time. You should be able to manipulate to come up with half-life if you don't happen to have access to something like that. You know, given everything else, I mean. You should be able to come up with the original activity if you're given what the current activity is. And all those manipulations, especially the coming up with the original activity and the final activity, you've already experienced how that comes into play. Using radioactive sources to do your equipment setup. You've got a source that you bought 5 years ago. You know what the activity was 5 years ago. But what is the activity today? That's that equation. Don't really sure when you purchased it, but you can tell what the activity is today, and you kind of would like to know, for whatever reason, fill out paperwork maybe. I don't know what the current activity is, or what the original activity was. That's the equation. So that's useful, and we just wanted to rehash where it came from and how we got there. Questions on the basic terms? That pretty much concludes the review portion of this. And as I said earlier, I think we're finding out that things like, had y'all ever been taught Avogadro's number before? Some of you have. Saw it before. You know, finding out, it's in Golnick, but he doesn't introduce it as what it is. He uses it and tells you what it is, but he doesn't use it for what it is. He uses it as an example of scientific notation, so he does. But he doesn't introduce it as being a standard or constant as far as number of atoms per mole or per molecule. And so I think we're probably going to add a little bit to 103 and kind of beat that up a little bit, just so they'll have the background. Questions on anything we've reviewed up to this point? All right, we're going to move into new material, and we will take a break about 6 o'clock. So we'll get started on this, and then take our break. That topic is equilibrium. Before I give you the definition, how would you define equilibrium? Just using that term, and the fact it has to do with radioactivity.
Out of balance.
Huh?
Out of balance.
Okay, out of balance or in balance?
In balance.
Okay, equilibrium would be a balance, right?
A balance.
Okay. Yeah, it would be a balance, and that's exactly what it refers to. We have so far only looked at radioactive decay from the standpoint of we've got cobalt-60 and it decays through some type of radioactive decay mechanism into another isotope. And in some cases, which is the case in cobalt-60, that daughter product is radioactive itself, and it will undergo. What we've not looked at is the instances where that parent and that daughter coexist. And in some cases, a lot of cases, they will coexist to a point where they will actually reach equilibrium values in your sample. Now, for longer-lived isotopes, that's not really a big topic. I mean, it's not a big issue from a radiation protection standpoint, because, especially if the daughter is long-lived. Because, you know, you do a sample and you've got a certain amount of activity and you've identified it as being this isotope, and you fill out your paperwork and you go on. But what if your parent isotope has a half-life that is reasonably long as compared to the daughter? And at X time, I say isolate the sample and I do my activity, and I come up with this many microcuries of that parent, and I come up with this many microcuries of that daughter. But what happens as that daughter is produced? We've got a parent with a long half-life that's decaying, so I've got atoms of that parent that are changing into that daughter, which means the number of daughter atoms that are there are going to build up. And if their daughters have a half-life that's sufficiently long or short, then the activity of that daughter may actually build up too. And so what I'm trying to illustrate there is I've got a point where I may actually have decided that, well, I'll tell you what, let me do this. This is what this is for. Wake it up, there we go. If I've got, and I'm plotting out activity over time, if I've got a parent that starts up here and it has a really long half-life, for say this amount of time being hours, but I've got a parent that has a half-life of years, what I'm going to be seeing in this time period is basically a flat line for that parent. It's decaying, but for what I'm looking at here, it's not going to be noticeable because the half-life's so long. Well, let's say at this time 0, that daughter starts getting produced. Daughter starts being produced. What happens to total activity in that sample? It's going up. And so if I fill out my shipping papers here, based on what I know that parent activity to be, and I don't take into account what that daughter is, then by the time it gets to where it's going to have more activity in it than what I say that it does. And then guess what? I'm in violation of DOT. So that's kind of why we need to understand equilibrium and the different types that there are, so that when we start getting into these isotopes that have a specific type of equilibrium, we'll be cognizant of this and we can actually anticipate. Now, is there software that does this for you? Yes, there is. But you need to understand what's going on. And you need to, again, understand why we do some of the things we do. Because that will happen. And ultimately, the production effect of this daughter, in this drawing, the production effect of this daughter in relation to the decay effect will equalize, and it'll also flatten out and appear to be fairly high activity. So what we need to know is where that time period is. And that will be the time max for the daughter. And we're going to show you how to come up with all that. We're going to talk about the different types. This is one. And how we can come up with some of the values that we need to be able to come up with in order to properly classify and categorize the shipments or storage or whatever it is that we're doing with it. So let's go back to the basics here. In radioactive decay series, we've already talked. The decay of the parent produces a daughter product. Radiation is emitted through that process, whatever decay mode it may be. The daughter also produces radioactivity if it is a radioactive daughter product. As it decays, it'll produce radioactivity as well. And that chain will continue on until you reach stability. Some of your homework had you taken isotopes from one level all the way to stability. Just get your practice doing that again. And in that process, we come up with this total collective activity that winds up being in our sample. Depending on the half-life, will depend on really how that builds up and what it comes up to be. But how much is contributed from the parent and how much contributed from the daughter goes back to really how those two half-lives compare. Now, in your reading, I believe you had Goldnick in edition 6. And if you're on edition 5, that is one thing that's not in edition 5. So transient and secular equilibrium. If you're on edition 5, I don't believe that that's in there. I think that got added with edition 6. So you'll want to go back and read that if you're doing edition 5. But that, he talks about 3 cases of equilibrium, and we're going to talk about those 3 here tonight. And it is dependent upon the relationship between the half-life of the parent and the half-life of the daughter. Now, we've already described this, but the official definition is when the amount of activity being produced is the same as the amount that is decaying, then we can say that a condition of equilibrium has been reached or said to exist. Balance was the word that was used. That's a good word. There's a balance there. Now you can see there are several types depending upon how the half-lives compare. The first one is secular equilibrium, and that's the equation for it. In this format, D is daughter, P is parent, everything else is just like what you used to see. Is the decay equation identifying parent and daughter this time. You'll also notice that it's a little different in that we have this, 1 minus. We'll talk about that. In secular equilibrium, you've got a situation where the parent half-life is very much, really a whole lot longer than what the half-life of the daughter is. And that goes back to what we were illustrating here. A half-life is really long. A parent, the activity will appear to be flat over a period of time compared to the half-life of the daughter. Mathematically, secular equilibrium is expressed as this. The activity of the daughter is equal to the activity of the parent times the quantity, 1 minus e to the minus lambda t, and it's the lambda for the daughter. Important. Lambda for the daughter. And the reason we can write it like this is because that half-life of the parent is so long that in essence over this period of time we're talking about, there has been no decay. And that's why we can represent the contribution from the parent with the 1. It's unity. No change. Now here's a common chain that comes into play for RP technicians. It is a fission fragment decay. Krypton 90 is a fission fragment of U-235. It decays to rubidium 90. It has 33-second half-life. So for the parent to go away in this case, in the case of the krypton, it doesn't take very long at all. So in a matter of an hours or so, 7 half-lives, several hours, it's going to be gone. But I've got this rubidium 90. Well, it's got a little bit longer half-life, but even with it, over a period of time, relatively short period of time, it's going to be gone. But what's going to happen here? Strontium 90 is going to be around for a while because of the half-life here. And so what we're going to look at in this example are this relationship here. The strontium 90 is going to be our parent. That's where we're starting. This is going to be our daughter. This is a pretty well-known relationship, strontium yttrium. If you talk to folks that are in the source business, making radioactive sources, they typically will refer to these a lot of times as the same thing. They'll say strontium yttrium. And it's because of this relationship. And it's because it is a secular equilibrium relationship, such that after a period of time, the yttrium is going to appear to be decaying at the same rate as the strontium. They're going to be in that secular equilibrium. So what did we just say? We said that the half-lives that can be seen, that activity of Krypton 90 will be depleted in 10 to 15 minutes, it's going to be gone. Now this is assuming I've got a sample and I go, isolate. Okay? So this is at time 0, boom. And then anything I observe from this point on is with it isolated, so that we can demonstrate these relationships. So 10, 15 minutes, Krypton 90 is going to be gone. Rubidium 90, which is the daughter product of the krypton, will be transformed within an hour or so. It's going to be gone. And we're going to be working at this level here, strontium 90. And all this builds us up to that rapid buildup of strontium 90. Now, starting there, looking at that relationship, strontium 90 is going to start its decay process, and as it does, it's building up a supply of yttrium 90, the daughter. And then the yttrium 90 will in turn also be decaying. It's got a fairly decent half-life, a little bit of 3 days, not quite 3 days. But it'll start decaying as well, and then the daughter there is stable. Zirconium 90 is stable. Now, because of that relationship, the half-life of the parent, in this case the strontium, is much longer than the half-life of the daughter, which is the yttrium, at 64 hours. Because of that, it will have, if we were to plot it at time 0 here, we will have the strontium looking here. And here, it's going to observe basically it'd be not decaying. The amount of activity that's there is going to be stable, or appear to be stable. But the daughter, if we start looking at yttrium at time 0 and start tracking its activity, it's going to build up to some maximum, and that's going to occur there. At that time is when we say that the secular equilibrium of strontium and yttrium has been reached. Any questions on that illustration? Okay? Let's work the problem then. If we start with 500 millicuries of strontium 90, what will the activity of yttrium 90 be after 5 hours, after 25 hours, and after 125 hours? Using that equation and your chart of nuclides or anything else that you can use to pull half-lives or decay, well, you should be able to calculate the decay constant that you've got the half-lives. Work out and tell me what yttrium 90 will be after 5 hours, 25 hours, and 125 hours. Go ahead and take time to do that. I'll tell you what, let's do this. Let's do this. See, I got 3 groups. 3 groups. Okay. This front row, y'all do 5 hours. Okay? The 8 of y'all do 5 hours. Okay? All right. Y'all do the 25 hours. All right? 6 of you do 25 hours. The rest of you do 25. 25 hours. Huh? Oh, I'm sorry, 125. 125. Thank you, Susan. Collaboration's okay. But everybody needs to work on this. All right, we've been working a little bit now, and I think everybody pretty much has an answer. For the 5 hours. For the 5 hours. After 5 hours, what's the activity of the daughter? 26.5. Okay, 26.5 millicuries. That's after only 5 hours. After 25 hours, what do we get? 118.5. It really depends on what you do with your exponent on your E, whether you round it or in interim steps, or if you calculate it all the way through. That will make quite a difference, actually. But around 118.5 millicuries. So that's after 25 hours. After 125 hours, what'd you get, Susan?
370.29.
Okay, 370 point, and again, 0.5, 0.9, somewhere in there, millicuries. Right. And it goes back and illustrates that graph, right? Here's what's happening. We have our parent, which is the strontium. And I had these guys calculate the activity of the strontium after 125 hours. What'd y'all get?
499.8.
Right. 499.8. So you can see during that period of time, we're looking at the daughter, basically a flat line. A little bit of drop, not much. But what we're seeing with the activity of the daughter is we're building up. Now, have we reached the maximum yet? What do you think? If it's going to be in secular equilibrium with the parent, what's the activity going to be? It's going to be about 500. Okay, somewhere in there. So if you, as a rule of thumb, let me go ahead and get these slides up there for you and make sure we get everything. The activities, the calculations, those are all on the slide for your review later. But that's the 5 hour, 25 hour, and then the 125 hours. And if we look at the parent isotope, and just do a regular decay equation on the parent, which was the strontium 90, calculate through that for the 125 hours that we did for the yttrium. Then we come up with 499.8 millijoules. Very little change.
So basically what we're getting out of this is after 125 hours, because of the daughter product, the activity doesn't change like it would have in the normal activity problem for the parent. Because the daughter, the parent's isotope is not showing the decay that you would expect to see.
Which one? For which one?
The parent. You want
Well,
to
the
see-
parents still show, I mean, it's still decaying. We
Right.
proved that, right?
I'm saying that you wouldn't.
But its half-life is so much longer than what the daughter's half-life is, that when we're looking at the buildup of the daughter, the parent's going to appear not to be decaying much at all. And in essence, for that time period, it doesn't decay as much. That's why it has a longer half-life. It stays around longer. Yeah.
So, from like a materials handling, if you were looking to ship this, would you just set the activity of the daughter equal to the activity of the parent and solve for the time and say I need to wait until this amount of time before I can ship it and it'll stay the same activity?
If only it were that simple. No, you're thinking along you're thinking along the same lines. What you've got to be able to do is come up with that time that maximum activity will be reached. And then you can go to that time and say, okay, at this time I will have this activity. And your computer program does this, but it will say, okay, and in this, it needs to know where that secular equilibrium occurs, what time that occurs. And then from there, it's just, where am I in relation to when I started putting this together? Am I beyond that, or am I still up to that point? If I'm beyond it, then I can determine what the activity is. If I'm not there yet, I can still determine what that activity will be and account for it. Does that make sense? That answer your question? Okay. So the activity of the parent appears to stay the same for that period of time we're looking at the daughter. But the question will be, when will the daughter reach that equilibrium? And the rule of thumb is about 7 half-lives for that daughter to reach equilibrium. So in this case, we're looking at yttrium with a 62-hour half-life, about 7 half-lives. What's that come up to? 400-something hours before it will reach equilibrium. So on my graph back here, that time is going to be at 7 half-lives.
That's the 7 half-lives of the daughter.
That's the daughter, right, right. Because that's what we're talking about, right? That's the daughter that we're showing there. So about 450 hours, it will reach the 500 millicuries or around that 500 millicuries. And we will say that they are in secular equilibrium. The yttring's not going to build up anymore. In fact, that's that point where its decay is equal to its production, and so it's right there. Questions? A secular equilibrium. Secular equilibrium. Say again? What's your question, Dan?
Why is it 7.5 lives for the daughter? Because if it goes to a half-life, wouldn't it decrease? Wouldn't the activity decrease every time?
Well, it's decreasing at the very beginning. It's decreasing from the moment it's born, but its production rate is that much faster, such that it will build up. Okay? So 450 hours, 7.5 lives.
So basically, producing the daughter, but at the same time,
The daughter is decaying, sure. I mean, nothing's put on pause here. All the physical laws will continue to function just like they've been designed to function. But what we're doing is illustrating that relationship. And again, let me say, this is a snapshot in time. At time zero, we isolate, and everything goes from that point when we're talking and illustrating here. Yeah.
So after that 7.5 lives mark, it'll steadily decay from
Nope.
500
Now,
mercury.
production will go, it'll look just like what you see there, because the parent is still around producing it, right? The parent is still there. So production's still going on. It's just that now decay has caught up with production, and you've reached this point at that 7.5 lives where that is in equilibrium as well.
Okay, so
Okay, so
decay and production.
Everything's in balance at that point. Right.
Before you change that screen, to find out the exact time, would you put 500 in for activity for the daughter and 500 in for the parent, and then figure out what time is? Do it mathematically?
No. That's where I was going, that's what I was telling Allison, I wish it were that simple. There is an equation we're going to get to at the end of this that talks about how to calculate that maximum activity and the maximum activity of the daughter. It shows you how to do that. It's related, Gary, it's just not that easy. Nothing's ever that easy. Okay, so that was secular equilibrium. Now we're going to talk about transient equilibrium. And transient, remember we were talking about it depends on the relationship of the parent half-life to the daughter half-life. In transient, it's where the parent is just only slightly longer than the daughter. Only slightly longer. I'm sorry, yeah.
Quick question. Would you ever come across a situation, say, the parent gives out a daughter, which is with a shorter half-life, but then that daughter creates another isotope that has, you get what I'm saying? That daughter is creating another isotope.
Yeah. Yep. If I'm, yes. This example we showed here, the yttring decays to the stable product. What you're asking is, are there cases where the daughter product will decay to another radioactive daughter? The answer is yes. Other questions? So transient equilibrium, slightly longer. And so if I take my parent again, and that phrase freshly purified parent fraction, that just means snap. That's time zero. Production of parent stops. We're looking at it from that point. That's all that means. So the daughter from that point will build up to a maximum, and from that point down, it will appear to decay at the same rate as the parent. There's a little graph that goes with that one. Let me get the equation up there first. It's referred to as transient equilibrium. And the mathematical equation for that, expression for that is the activity of the daughter is equal to activity of the parent times the quantity of the decay constant for the daughter divided by the decay constant of the daughter minus decay constant of the parent. And again, if you really want to know how that came about and how it's derived, I'll gladly loan you this book, and you can follow him step by step. Because he knows. I don't know if you ever heard of Simber or not, but Simber is the man for HP. And he does a great job of stepping it through. He does a really good job. So if I were to plot what I just said there, and again, this is time, and this is activity, and I'm going to start with some parent activity right here. And I'll isolate my sample, and I'm looking at it, boom, at time 0. That parent will start decaying away, and we're going to go radioactive decay, and we'll show, this half-life here. And we'll say that that's my parent decay curve. The daughter, starting at time 0, is 0, will build up rapidly and then reach a maximum and start decaying, and its decay rate will appear to be the same as the parent. That's the daughter. That is transient equilibrium. Transient equilibrium. There is a decay chain that occurs in nature, and you folks have been working with it for some time, that illustrates this, and that's in the natural decay chain. Lead-212, I'm not sure which one this comes from. It comes from one of the natural ones. I didn't capture which one. It's either the thorium or the uranium-238. But anyway, there's a decay chain in there. Lead-212 decays 10.6 hours to bismuth-212 with a 60.5 minute half-life. Decays to thallium with a 3.1 minute half-life on the lead-208. This particular one, if we have and this is the parent that I'm looking at. This is where we start on this one, this parent. And what we're going to look at is the equilibrium relationship between the lead and the bismuth. Its half-life is longer than the half-life of the daughter, but not real longer, as was the case with the secondary equilibrium. So let's take an example. Let's say I've taken air sample, and I've calculated it out, analyzed it. I've got 5 picocuries per cc of lead-212 in it. The question is, what is the equilibrium value for bismuth-212? And you should be able to work that just using the equation I gave you there. I want you to go take a couple of minutes to work through that. I think everything you need is right there on the screen. You've got the half-life expressed. You can come up with a decay constant from that. timekeeper let me go past break time. Tell you what, let's go ahead and take our break. We'll come back. You can finish working on this between now and then. We'll come back at, we'll start discussion again, let's put it that way, at 6:30. That way you have a little bit more time to work on it. Hang on, yeah.
When working on this, does the unit times have to be in the same?
Units must be consistent. That answer never changes. I promise you, it will never change. We're calculating the equilibrium activity, or what it would be for the daughter of the lead. 212.
This is a minus sign.
What would you expect the equilibrium activity to be? Without doing any calculations?
About the same.
About 5, right? About the same. 5 picocuries per cc. And hopefully in the calculations you came up with, working through it here, 5.5 picocuries per cc. Of the bismuth, that's the activity of the daughter.
Sorry.
Really, it's just an exercise of a different expression of the activity decay equation, taking into account the nearness of the half-lives of the two. Questions? Everybody get through that? Okay. Oh, okay. There was some question about the half-life that's used here for the bismuth. If you look in the chart of the nuclides for the bismuth, you actually have 3 different things going on there. You have 3 different types of decay. And if you split it out and look at a decay scheme of bismuth, you'll see that it goes 3 different ways. 65% of the time it goes the direction what you're seeing here. And then the remaining time is split between the 2 other mechanisms. It's not uncommon in looking at a single isotope decay path to take the longest or the longer, depending on how many options there are, half-life, or the one that's most prevalent. If any of you are interested, I think I may have announced it to y'all, there is an optional resource in the bookstore. How many of you seen that? It's not that thick. It's the modern day version of the Rat Health Handbook, which I think you guys have had made available to you anyway, electronic versions of it, ever since you started. But it's from the 1970s, and this new updated version is quite a bit better organized and easier to find things. It's not cheap, but it's a good reference to have if you're looking at staying in this profession. And the reason I bring that up is you can go there in Chapter 8, and it basically will show, it shows all the nuclear data for all the isotopes, everything. The different types of decay, percentage of decay that bismuth with 212 would go in this direction, that direction, or the other direction. It's a pretty good resource. Yes, sir.
I thought we were told that the decays are actually listed as far as what's most probable to happen.
Decay modes.
Yeah.
Yeah. That one goes, it splits 3 ways.
It's got 3 different windows in it.
Yep, it does, because it has 3 different ways it goes. Not too many to have 3. There's some in there that have 2.
But see, even then, it says here, the way you talk about beta minus is the most probable way.
Okay.
But yeah, that's not a.
No, that's an alpha decay there.
Yeah, that's what I'm saying.
Let's see what it shows.
This is beta minus is the top one, so that's the most probable.
That should be. That's what we showed you. I'll just take that in. I took this as an example from Sember, so I didn't really check
Now
details. I mean, and we're just using it for illustration purposes anyway. So, but yeah, that's very inquisitive. Thank you for checking on that. You're absolutely right. I'm not sure what he had in mind, other than was he is describing the alpha decay path for a reason that he may be. Okay, everybody finished doing their calculations? Get something similar to 5.5 picocuries, which is what we would expect to see, about the same amount because it's equilibrium. But then we go back to the question we've been asking since we started all of this, and that is, when does that occur? When does that equilibrium value, when does that maximum daughter value occur? So that's going to be our next topic, is how to come up with that information. Before we move on though, any questions on secular or transient equilibrium? There is another case we're going to talk about, but I'll talk about it after we talk about calculating time. Yes, sir.
Is there like a guideline for how long the relative half-lives have to be, whether it's transient versus secular?
What does a whole lot mean?
Yeah.
Yeah, no. There's no guidelines. It'll be evident from a problem-solving standpoint for testing purposes. It'll be evident. And someone else has asked that question, and you know, what you get used to is you know you run into strontium and yttrium a lot, because it comes from the fission products. And so if you're working power plants, that's a common pair of isotopes that you see. You know that it's going to be undergoing the equilibrium, secular equilibrium, and so you just know that's a secular equilibrium relationship. These are naturally occurring. We run into them all the time, so we're going to know when we get down in those decay chains occurring from naturally occurring radioactivity, it's going to be a transient equilibrium relationship. So what I'm saying is, as you do this, you come up with those relationships that you know occur, and so you don't have to make that judgment call. But as far as our testing purposes, it'll be evident. It'll be evident. Good question, man. Thank you. Any other questions? Okay. So let's talk about time. Let's talk about time. In that, we'll continue using the same example. So in the time after we isolate, we start that time zero, we can come up with that time that the daughter will reach the equilibrium value, or the maximum activity value, that we expressed on the curve. The equation for doing that is this. It's the time for maximum daughter. That's what the MD stands for, maximum daughter. And everything else we used before. Oops, that should be a P instead of a B.
P.
If I see that, that should be parent. So we got the natural log of the lambda for the daughter divided by the lambda for the parent, divided by the difference between the lambda for the parent minus the lambda from the daughter. Okay. We're going to have to do some adjustments here. That needs to be, and I'll write it here on the tab. When the reference I used was December, he uses A and B the A is the parent, and the B is the daughter. And so when I transposed it, I started using parent and daughter because that was kind of a learning aid. But I forgot to convert it. So what that should read, and I'll make changes on the PowerPoint. That's what that should be.
Better than the food transfer?
Sorry.
The T and the D and the B?
No, it's worse than that. It's down here on the bottom.
Yeah, you got skirted around on that one too.
Yeah. The top part of it was right, so the bottom part was sloppy.
D minus P for the bottom.
Lambda D minus lambda E. Delta papa. Everybody get that? I want to make sure everybody got it. Okay, and I'll have to make changes to the PowerPoint. Okay. I'm not sure how that affected the example. We'll see. Okay. So that should be lambda daughter minus lambda parent. So let's use our example. Work through and find this time. Our equation, which should be daughter minus parent down here on the bottom. We know lambda, 0.693 divided by the half-life. So the lambda for the parent up here, lead 212, half-life 10.6. So the lambda value for the parent should be 0.065 per hour. Likewise, lambda for the daughter, 0.693 divided by the half-life. Units must be consistent. So we'll go ahead and make that transfer now, which is 1.01 hours, 0.686 per hour. Good news is my calculations are right. Yay. So if I plug the values into the equation, which are really the lambdas are the only plug-in values, do the math, and we'll come up with 3.79 hours. That's the time in which the daughter activity will reach its maximum value.
You did say on the bottom of that formula, in the denominator, the correct version is the decay constant of the daughter minus the decay constant of the parent, correct?
Right, daughter minus parent.
Okay.
That's correct. That's what I'm saying, the math is right, the example is right. Just that, yeah, the stated equation was written down wrong. So what I'm looking at, when I look back to my graph, that's the value that occurs. Maximum activity of the daughter occurs at 3.79 hours. ask you this question. Yeah, Allison?
I didn't see where you wrote that for a second, and I did the, where it was a B, and you said that was supposed to be, I thought you said a P. I did the parent minus the daughter and got the 3.79,
Really?
because I didn't see that part. I
Okay.
just did the calculation, parent minus daughter.
Let me,
I don't know. So I thought you were just saying the B was supposed to be a P, and that the D was.
well, that's what I said initially, and then I realized that it was actually
They were
swapped.
both swapped.
That part's right.
It just looks.
Top part's right. So my numbers in my example are right. Up until the last division. So let me do that. I got 3.79. Anybody else work it?
Yeah. You're right, just I agree with you.
So you got the 3.79 by using the parent here?
Yeah, I mean, I got 3.78
Using the parent
by
here?
using parent minus daughter.
0.065.
Well, I didn't calculate it out to round. I did it.
Well,
I
that's the
plugged
value
in.
for lambda for the,
Yeah, I did natural log of 2 over the half-life and just
Okay.
put the whole thing in at once without any rounding in the
How do you do all
calculation.
that once in a second?
A lot of parentheses.
What about that?
okay.
I don't know.
We'll work through the mechanics to figure out how that happened, but this is the right
Could have been
answer.
dumb luck. I might have put it in wrong.
This is the right substitutions,
Okay.
okay, in the right equation. And this is the right answer for what we've got here. So we can come up with that value. That's the value of when the activity of the daughter reaches its peak. That's where that curve makes that crest and then starts coming back down. But when we're doing shipments, a lot of times we need to know the total activity. So really it would be useful to be able to say, well, the total activity will occur at a certain time. Let me take you back to the little graph. At this time right here, 3.79 hours, is that the time at which the total activity is at its maximum? Total activity would be the addition of the two lines. Who says it is? Is that the point at which the total activity would be reached? Or is it some other value?
Most likely some other value.
So since there's
Oh, it
no
would be acid,
equation,
right?
That's just
It is some other value. Because if I add those two numbers, I'm going to come up with a value that's not the maximum. Okay? It would be somewhere in between here. It would be a value right there. And you can already see I've got a maximum that's much higher than that over here somewhere. But I'm looking at the activity of the daughter plus the activity of the parent to come up with that maximum. So let's go back and take a look at an equation that will help me to do that. Because I do need to be able to do that. Parent plus daughter activity, I need to know when that activity occurs. And dadgummit, it's there too. And that's the equation. And it's the same problem on the equation. Where you see this B, that part's swapped. It should be lambda daughter minus lambda parent. I just cut and paste those equations. So that part of the error propagated through the
But the second one, is that right?
error propagation. Oh, maybe that right.
Is the one in the parentheses okay?
This is what you call blunder. I'm sorry.
Is the section in the parentheses correct?
Yes.
landed daughter minus landed parent?
Yes, this is correct. This is correct. This is the only error. It's the same error we had earlier. It should be lambda daughter minus lambda parent. I make that? Everything else is right. I do apologize for the blunder. Yeah. So if I go back and use the same values that I used earlier for the lambda for the daughter and the lambda for the parent, it's the same two isotopes, right? So I can do that. I can use that value. And that was 0.065 for the parent and 0.686 for the daughter. And I plug those in and do my calculations. I'll come up with the time at which the maximum total activity will be reached. Time for the maximum total activity. Take a couple of minutes and get that. Trying to figure out how we could come up with that.
Somehow or another, I ended up in the calculator. I was wrong. It came out wrong.
What'd you get on this one?
Everything just
Okay. same as the parent. I'm sorry, the daughter minus the parent. That's what I'm saying, that part of it's wrong. It should be daughter minus parent.
You know,
Is it active? What are we talking about? That's the T, the little T is what? The T there, and that T, M, big T.
back when we looked at it, we got back to the you said you had both bodies to look at it.
Okay, I think most of you are there, and you're getting there pretty good. The time calculates out the time for the maximum total activity to occur will be 2.76 hours. Less than what the time for the maximum daughter, right? Which was 3 something. If you look at the graph, go back to the chart, see that illustrated. This is when that peak there occurs, but the peak, the time when the maximum total activity occurs is going to be sometime less than that, because the declining or the decreasing parent activity. So it will be before, probably that intersection of those two. So those are 2 quantities that you can determine, 2 time periods, 2 mile markers, if you will. When you're working the shipping papers, you have to take that into consideration. Where am I in that timeline? Have I reached that point where my shipment, my sample, whatever it is that I'm moving or transporting, has it reached that maximum activity? And if it hasn't, then I need to figure out what that maximum activity is going to be. And we can do that through what we talked about as far as reaching equilibrium. Those are the 2 basic ones. But there is another situation. Any question on the time calculations? Other than please make sure that you make this correction on your notes, and I will make the correction in the PowerPoint. But this should be daughter minus the parent. Daughter minus the parent. And again, I apologize for the blunder. Now, if I take a look just at the daughters of both of those and put them on the same graph, you can see what happens here. The secular, this is just the daughter plots, okay? The secular daughter will build up here and eventually reach some constant that appears. The transient daughter, because of the half-life relationship, will make that go straight into decay, and it will appear to follow the parent's half-life. Those, I believe, that graph there is the one that Golnick uses as he illustrates. There is a third situation, looking at parent half-life compared to daughter half-life, and that is where the parent half-life is less than the daughter half-life. In that situation, basically, we're looking at a no equilibrium situation, and will not reach an equilibrium, because the daughter will decay away, build up a supply of daughters. The parent will decay away. In that process, build up a supply of daughters, which will in turn start to decay after the parent's gone. After the parent plays out and decays away, then the daughter will do likewise. So what we'd say there is when that occurs, when the parent half-life is shorter than the daughter, the 2 never reach a sustained state of equilibrium. Daughter builds up to a maximum and decays away. Parent starts at its maximum and decays straight decay away. And that's about all we'll say about that. There's no special calculations or formulas for you for that situation. And that basically ends the lecture series, or lecture portion of the lecture on equilibrium. Questions on that part? Yes?
For the no equilibrium situation, does it matter if they're fairly close? Like you said with the transient, if they're fairly close, but the parent still has to be longer?
For a transient to occur, if the parent's shorter, then there's not going to be an equilibrium situation.
Even if they're pretty close, like if it's just a little bit shorter?
Yeah.
Okay.
Never happens. Other questions? Okay. As I said,